please, is a slide of Professor Gurgel. The talk of Professor Gurgel, small satellites-based mission for the Brazilian Aerospace program. Professor Gurgel is a professor at the Department of Mechanical Engineering in Brasilia, University of Brasilia. Dr. Gurgel has undergraduation in mechanical engineering from Universidade Gama Filho in 1985. He worked for 6 years in the industry, mainly as manager of industrial maintenance and projects. He completed a master's degree in aerospace propulsion in 1991, and in 1998 he completed a postdoctorate program at Combustion and Propulsion Laboratory at INPE. In 2006, he completed a second postdoctorate fellowship at the College of Forest Results at the University of Washington in Seattle. And now he is currently Director of Satellites Application and Development of the Brazilian Space Agency. Then I will pass the word to Professor Gurgel.
So,
thank you.
Thank you very much. First, I would like to thank the organization for this opportunity. It's always nice to talk about our space program, and then specifically, I will address my talk to small satellite missions that we are planning, and some are just happening right now, okay? As you can see, we start doing satellites in Brazil in the late 90s. These two first satellites, they were built to do what we call data collection system. I think the second one is still operational, though like maybe at 20 or something like that in performance. But it's good to know it's more than 20 years they are still working. And then we start a program in cooperation with China and start building bigger satellites for remote sensing. This is what we call the CBERS program. Right now we have a satellite that is operational, and we are finished the next one. And we are also discussing the future of our cooperation with China. So this is the satellite I just mentioned, which is operational. In 2013, we launched CBERS 3, but unfortunately, there was a failure of the upper stage of the Long March launch vehicle, and then it was a horrible story because we were following the launch, and then we got the message from China that everything was okay. So we went, that was something like 2 in the morning, and then 8 in the morning, the press was all in the space agency because of the failure of the launch. So we lost the satellite. And some people were asking if we could recover and launch it again. And as you know, it just disintegrates. But we work hard, and then a year later, we launch CBERS 4, which is this one, and it's operational for maybe 2 years more. We just launched our communication satellites geostationary couple of months ago. The commissioning phase has finished. Satellite is fully operational. For those who are following what has happened, this is a very big satellite, 6-ton satellite with fuel. The satellite was meant to provide a security communication for our defense system, so X-band. It's about 20 to 25% of the transponders, and the remaining is for broadband communication, Ka band. I don't know if there is someone from Telebras here, but there is, they proposed a business plan for this satellite to rent, let's say, about 70% of the Ka band for those internet providers and so on, but it fails, and then we don't know what's coming. But in any case, this satellite is fully operational, and it's the Air Force controls the satellite. Okay, it's the lifetime expected is more than 18 years. So now I'll show you some projects that we are developing, and we have Sibers 4A on the left. It's a satellite that's about 2 tons, so this is not a small satellite. I will classify them quite in the next slides. And then we have Amazonia 1, which was supposed to be a small satellite. The Amazonia 1 satellite is for remote sensing, but more importantly, the mission was designed to qualify what we call the Brazilian multi-mission platform, which is the lower part of the satellite that we call bus, platform, or service module. In the upper part, we have the payload module. In this case, it's a wide field camera built by Optoelectronics in Brazil. And this camera is very good, but also very heavy. So the satellite ended up with more than 700 kilograms. So now I'll show you a couple of slides on our initiatives for small satellites. Most of them, they are educational, and the purpose, of course, is to qualify human resources at the university level, so they have opportunity to design the mission, and based on COTS components, off-the-shelf components, they are able to integrate a small satellite and then operate it for a couple of months, and this time span should be less than 2 years in order that you don't frustrate the students. So we have a history of Itasat. Itasat was designed, and they were working on the project for more than 12 years, and still there was no satellite. So when we came to the space agency, we corrected that by asking them to work on much simpler satellite, okay? So we, this one was launched on 2014. It's a CubeSat, 1 unit, and it was a scientific mission. Somehow it's still working, sending some beeps. The second one was built by ITA students. We launched it from the International Space Station, from the Japanese module, but this satellite didn't work. And then we have good number of satellites that we supported. So as you can see, Itasat now it was a much bigger satellite, and it ended up as being a 6-unit satellite, what you call nanosatellite with 6 cubes. Okay, it's gonna test some technologies like onboard computer, code, and a transmitter, a transponder for our data collector system. Okay, it's the same transponder that we have in Sibers and also in those small satellites we launched back in the 90s. We have the 14 BizSat. This one is one of the satellites of the QB50 mission, and from Germany. And there is something that they have been delayed the launch of this constellation of 50 small satellites. And then in the right we have the Serpens one. So the Serpens was built and coordinated by University of Brasilia, the Aerospace engineering course. It's a 3-unit satellite, and they were able to, from phase 0 to phase E, so the whole lifetime of the satellite, to accomplish the mission. And that satellite was also launched by the International Space Station. It worked for about 6 months until entering, and then of course it's over. The International Space Station is orbiting at about 400 kilometers high. So for a small artifact, there is some drag. There are some molecules that are decreasing the speed of the satellite, and then in about 6 months, we expected that the satellite will re-enter, and that has happened. And then in the right, we have Ubatuba-Sat. It was a small satellite built by students from a school in Ubatuba. So that one was also launched by the International Space Station, and this one re-entered a couple of weeks ago. We got the tracking system that show us. So based on that, we come up with the idea of creating a program for small satellites that we call Serpens. And what we want to do is system engineering, hands-on, in our space engineering courses. We also provide access to space, development of subsystems, capacity building in a broader sense, and we want to consolidate a small sat culture in Brazil. So one important thing about Serpent is that we want the mission to take place in less than 2 years. That means all the components, all the subsystems, they should be already available. So we call it in the NASA metrics, we call the maturity of the technology. The technology should be above 6, okay? There is no development of subsystem as you run the mission. All the components should be available, and then the team should only concentrate on building the satellite, okay? By that means we are sure that when a student in his period at the professional part of his course, he can start and finish the mission, okay? So I'll talk a little bit about what's going on, and we call it a new space for those who are not aware or do not follow space programs. So the mass of the satellites are decreasing very rapidly, and of course we know the reason. The electronic components, they are shrinking. We know that because of this. This is for instance, one of the driving forces that provide us with a lot of components that are very, very small and very, very powerful and efficient, okay? One example, a real example, is this company called Planet Labs. This satellite, as you can see, is this big. There is a reference just beside the satellite. So they have now 167 satellites orbiting. There is no launch provider for small satellites, a satellite that small. What I mean is that you cannot plan a constellation with specific orbits because there is no launch vehicle. So those small satellites, they are launched in a way that we call piggyback. So there is always the main payload of the mission, and then after this big satellite is released, we release a lot of small satellites. For instance, India has launched a couple of months ago more than 100 satellites, so a big one, and a dozen of those small artifacts, okay? So that means you cannot think about a real constellation. So what they do is they populate, the space with those big numbers of satellites, and then they can work as a virtual constellation. This constellation is now able to provide images of the Earth every single day. So this is quite uncommon. And the resolution is less than 5 meters with a 5-kilogram satellite. This is something amazing, okay? A second example is from OneWeb. It's a company that is planning to do communication not based on geostationary satellites, but in low orbit satellites. So it's going to be 900 satellites. The mass is about 150 kilograms, so we call it, it's classified as a small satellite. And you can see a picture of how many launch vehicles. That one is Soyuz from Russia to deliver the constellation. Now, this is going to be dedicated flight to put those satellites in the desired planned orbit. For instance, only the launch is it's a $1 billion contract. So another thing about this satellite is that, so since they need now about 900 satellites, and also they have to keep the constellation working, so they have to replace those that are having problems or the lifetime just ended. So they built a robotic system that those satellites are built almost automatically. This is something quite new in the space sector. So Brazil, as you might know, we have very low budget comparing to many nations, and also we are facing economic crisis. And another picture I want to show you is that Brazilian multi-mission platform. If we think about a satellite weighing 500 kilograms, if you go to the market to contract the launch service, you have to pay something between $20 to $30 million to launch this satellite. And we don't have right now a launch vehicle that's capable to do that. So now what we are analyzing is how to escape from very big satellites that need many years to mature, a bunch of people working, a budget very high, and so on. So we are now looking for this new space era, and then trying to combine those technologies to take the most to our space program in different applications and services and so on. So all those satellites are classified as small. So the moon mission would be around 500 kilograms, but we have also microsatellites and the nano one. Nowadays, we are trying to combine satellites based on this multi-mission platform and going down to nanosatellites. One example is that we studied a mission in cooperation with Argentina. It's an ocean color satellite based on the multi-mission platform. The idea is to have two satellites doing images of coastal areas, oceans, and so on. We have the Equus mission. It's a scientific mission. And this one is based on a 150 kilogram platform. We have a problem because we don't have such a platform. So we have to go to the market and see who can provide the platform and then integrate the payloads, okay? And the payloads are quite many. You can see GLOW, GROM, IONX, ELISA, and APEX. All those payloads integrated in this 150 kilograms satellite. And then we have now ITA has developed that 6-unit satellite platform, and then NASA has come up and is doing a cooperation for this scientific mission based on those very small platforms. Okay, it's about 5 kilograms satellite. So we also have a code from the Aerospace organization that we can do cost estimating of those missions. And this is very important because the program can say how much is going to cost all the subsystems. And also it provides you a funding profile and the cumulative profile for that mission. So we now can have a better idea how much it will cost missions based on small satellites. The code actually is quite simple, but what's very important is that the data that is give the numbers for the code, they are always being updated by this organization, so they are giving us a good idea of the price of such a mission. And then you can see here a forecast of the expected number of small satellites that's going to be launched in the next year. So we are talking about hundreds of satellites. And as I mentioned, since there is no launch vehicle dedicated to launch small satellites, so many companies are trying to develop such system. And as you might know, launch vehicles is a very complex technology. Liquid propulsion is something that few countries have the full domain of the technology. So, but there is a target price and how much it would cost a launch from those small vehicles. We are talking about something less than $50,000 per kilogram of satellite, okay? So based on that, my team, so even though we are in the satellite directorate, we have specialists in my team that we, from University of Brasilia, that we sent to Ukraine and also to France. So they have a very good idea about the whole system. And also they brought codes from Ukraine. And because of that, we are able to do assessment on how it would be a launch system for those small satellites. So what we did was we measure the performance of the vehicle using this Ukrainian code from Dnipropetrovsk University and a transcost model from Germany. So, and then we could have a good idea about the development cost to fabricate, and operational costs of the launch system. And the next criteria was we should use the S50 motor for lower stages. This motor is being developed. It's a 11-ton propellant, solid propellant motor that is being developed by the Air Force. So we set up those configurations, different configurations. I want to go in detail, but then we came up with two solutions. As you can see, so we have three big motors for the first stage, a second motor for the second stage, and another solid motor for the upper stage. So combine those motors, you could go up to 400 kilograms launch at a 600 kilograms reference orbit in sun synchronous. So this is polar orbit, okay? It's sun synchronous means that the satellite will pass at the same time at the equator every day, okay? And those motors, they are being developed or they are ready, space qualified as the S44 motor in the upper stage of the first example. And then a second configuration, we changed the upper stage for a liquid upper stage based on storable propellants. For those who are not aware, most of the launch vehicles, they should have a very small motor. It's not powerful because those lower stage, they do the job of escaping from the Earth and then bringing the system to the orbital velocity that is necessary to stay there. But we need to control the insertion of the orbit. To do that, you should rely on liquid propulsion because you can increase and decrease the thrust, and you can also shut off the motor, wait for a while to do circularization and those maneuvers, okay? And the good thing about this upper stage is that all the components, they are off the shelf. So we could go to the market and identify the tanks, the valves, and even the small motors that you can see down. They are 15 kilograms motors, and we have 4 of them combining, giving us about 10 kilonewton of thrust, okay? So with this configuration, it was very interesting that we could go to a satellite as big as the multi-mission platform at 600 SSO. And I forgot to put the numbers. This second configuration would charge about 40,000 US dollars per kilogram to launch in a dedicated orbit. So by that means combining this launch vehicle and our multi-mission platform, and also taking advantage of those nano and small satellites, we could give a different picture for the Brazilian space program. And I can tell you there are so many technologies waiting for opportunities, like communication, like radio defined by software and so on and so forth. Please try to follow this, because in the near future, many opportunities will come because we are trying to increase the number of missions based on those very small platforms, okay? So that's all. Thank you.
Thank you, Professor Gurgel. We have time for a short question, please. your name and institution, please.
Konrad Nieradka, OHB system. I have a question regarding the Serpens program. You said that you want to involve the students and do it in the 2-year time frame so that everybody can live in the university till the launch. But what kind of technological background will you use? Do the universities have this background, or will you also cooperate with the industry?
Okay, good question. So when we start the program, we had the support of Professor Chantal. Professor Chantal is a lady from University of Brasilia, our aerospace engineering. She proposed this program and the first mission, and she was able to do everything in 18 months. So Professor Chantal used to work with Dr. Bob Twiggs. Bob Twiggs is the inventor of the CubeSat standard. And so the idea is that the university doesn't do any development. So all the components should be in place. And then they should practice what we call system engineering, how to integrate. So we have now, I would say, a small community in Brazil that is able to follow such projects. But more importantly is that the space agency now has this knowledge. So in my team, I have 3 or 4 guys that can follow the development of the satellite and do any intervention that is necessary in such a way that they can get the satellite ready on time. Okay, so we are a sort of we call design authority of the satellite. So we give the opportunity, but still we are the design authority. Okay, we can do that, no problem at all. And of course, the industry can follow what's going on, but actually this is mostly for the professors and students at that specific university that's coordinating that specific mission. Okay.
Unfortunately, we have no time to other question because we have delay. Thank you, Dr. Gurgel.
Thank you for the opportunity.
Presentation. It's very interesting.